Welcome to my calculus tutorial on Leibniz and Newton notation for the derivative. Topics I want to cover are Sir Isaac Newton and his notation of the derivative in calculus, and the other one, which is more commonly used, Gottfried Wilhelm Leibniz and his notation on the derivative in calculus. Isaac Newton developed the calculus during his study of motion and time. This primarily occurred in the 1660s when he was off from Cambridge because of the plague, so he was trapped at home for over a year, and he introduced this concept of fluxions to represent the instantaneous rate of change of a quantity. Newton used what's called the dot notation to express time rates of change. So in Newton's notation, the velocity is equal to the first derivative, or x dot, of the position of an object. And the acceleration, which would be the second derivative, would be represented by x double dot. Newton's notation is more commonly seen in the study of physics rather than just in calculus and mathematics as general. The second notation, which you will see more prevalent in mathematics, was developed by Leibniz, and he was from 1646 to 1726. Leibniz and Newton basically were contemporaries of each other. He's from Germany and Newton lived in England, so they only corresponded with each other. To Leibniz, he viewed calculus as a symbolic and general analytical tool, applicable to more than just time-dependent problems. He introduced the notation based on the infinitesimal changes in variables. So dy dx is the first derivative of y with respect to x. So if we substitute y is equal to f of x, then the first derivative is equal to f prime of x. That's another notation you'll see, the prime notation. So we also use this prime notation for y prime or f prime of x. So there's many ways of representing this derivative, and sometimes it's confusing. That's why I wanted to go over this, because I remember back in my early days when I first saw some of this, I got confused sometimes about what they're exactly trying to say. So we can write the derivative of a number, such as this would be the first derivative evaluated at 2 as dy dx evaluated at x equal 2. So the vertical line is interpreted as evaluated at, so the expression is read as the derivative of y with respect to x evaluated at 2. So here's some simple examples of the derivative of some functions that you'll see. The first derivative of x squared is equal to 2x. The derivative of x cubed is equal to 3 times x squared. And the derivative of 1 over x is equal to minus x squared. And you're going to see many more in your career in calculus. I want to thank you for watching this short video. Hope you got something out of it. If you did, give me a like, a comment, subscribe to my channel, and there's some more information in the description of the video. Thank you.